Hello, I see you're back for more. Though before we progress, I'd like to clarify something about the sigma notations that were introduced in the previous video. If you've ever encountered the symbol before, you're probably aware that it refers to sums, but the way it's used is different. And you'd be right, because the way the sigma is used traditionally is different from how we use it here. In this chapter, the sigma notation is simply a shorthand representation of certain combinations of sums, whereas the traditional way of using sigma is a distinct and detailed summation of a series. For example, the normal way to use sigma would be to have an expression, say x to the power k, inside the sigma, and detailing how our iterator variable, which is k, behaves, which would be to start from 1 and end at n. So if we were to expand this, we would have this expression being summed to itself, where each passing term has an ever-increasing value of the iterator. Essentially, what you end up getting is the sum of a series, whereas our sum of alpha would be a sum of combination of roots, which also depends on the degreeth polynomial we're dealing with. Hopefully that clears this up and avoids confusion for when you'll encounter sigma in other topics. And with that, let's get back to the video.
Hey, now that we know about sums and products of roots, we've pretty much figured out how to get polynomials easily, right?
Yes.
So we can stop now, right?
Oh no, we don't stop. This time, we raise the sums over powers.
How many powers?
All the powers! So yeah, because some genius had nothing else to do but to play around with math as if they were Lego pieces, we are now stuck with BS like this. They thought, if the sum of roots is minus b by a, what's the sum of the square of the roots? To do that, we'd have to perform a squaring operation on the sum of the roots itself. Keep in mind that the sum of alpha squared and the sum of square of alpha are not the same. Assuming we're dealing with quadratic equations, the former is substituted like this, whereas the latter is substituted like this. For the sake of clarity, I'll be calling the first one as sum of alpha whole squared and the latter as simply sum of alpha squared. Now, the sum of alpha whole squared is expanded exactly how you would expect a binomial expansion to take place. Once expanded, all we have to do is rearrange them for our convenience and boom, there you have it. If you swap them around, you get the answer to our original question, which is sum of alpha squared equals sum of alpha whole squared minus twice of the sum of alpha beta. And this is one of our main formulae you'll be using throughout this topic. Once you have this formula, you can simply replace these terms with their respective coefficients to evaluate specific situations. Now the question arises, does this also apply to cubic equation? Well, let's test it out, shall we? We have the sum of alpha whole squared, substitute it appropriately, perform a trinomial expansion. By the way, if you've never done a trinomial expansion before, it's no different from a binomial expansion. Just treat any two terms as a single term and perform a binomial expansion. Then, perform a binomial expansion of those two terms themselves. Expand the rest, group them up and arrange them, perform the substitution to our notations, reorder them, and here you have your answer. Now another question arises. What if we want the sum of alpha cubed? Same deal. For simplicity, I'll pretend we're using a quadratic equation. Write down the sum of alpha whole cubed, substitute, perform a binomial expansion, group up and rearrange. Now here, you might be tempted to write this as sum of alpha squared beta, but that would be a dead end. Remember, we can only substitute to terms that we are already aware of, such as our base sum and product of roots. For that, you need to perform this little factorization trick. Now we can perform the notational substitution. Reorder them, and here you have another main formula that will be used very often. So remember, whenever you encounter a situation like this, always try to factorize and see what it gives you. Now you can also ask the same question as before for this. Does it also apply to cubic equations? But I'll leave that to you to figure out. Go ahead and play around with it. What we should really be asking is this. Sure, we can go up the power ladder, but what if we go downwards? What if we want the sum of alpha to the power of -1? Or in other words, what if we want the sum of 1 by alpha? Well, if your first instinct was to think of writing the sum of alpha whole to the power of -1, you'd have fallen into a trap.
It's a trap!
You don't actually need to do that in this situation. Simply write down exactly what you're supposed to figure out, perform an LCM operation for the fractions, then perform the notational substitution, and thus you've encountered another formula that you'll need to memorize. However, don't be fooled. Despite the sum of alpha squared being the same in quadratics and cubics, the sum of 1 by alpha is a completely different story. We should never jump to conclusions in formulating things in mathematics. It's alright to assume, but always prove it before you can conclude your assumptions. If we try to derive the formula for cubic equations, we'll be starting the same way as the quadratics. After performing an LCM operation, we end up with an expression like this. And if you're quick to recognize this pattern, you'd be correct to conclude that the substitution in the next line would result in this. Going by this logic, if we recall what the sum of 1 by alpha was for quadratics and compare it to what we got for cubics, it would imply that the formula for quartic equations is this. But then again, remember, it's alright to assume, but do not conclude. While you're more than welcome to verify this on your own, this is as far as I'll be going with this. Moving on, finally, while this will seem kind of pointless at first, it's also important to know the sum of alpha to the power of 0. If you're using a quadratic equation, the substitution would be like this, giving an answer of 2. If you're using a cubic equation instead, the answer is 3, which means that the sum of alpha to the power of 0 is equal to the highest power in your nth degree polynomial, which I suppose can be written as this. We'll be exploring more where this is useful in the next video. Now for some examples. It's given that for a quadratic equation whose roots are alpha and beta, alpha plus beta is equal to -3, and alpha squared plus beta squared is equals to 7. Find the value of alpha times beta, and also find our quadratic equation. Now first things first, since it's given that alpha plus beta is -3, we can rewrite this as sum of alpha equals -3, and the same thing goes for alpha squared plus beta squared, which is sum of alpha squared equals 7. Now remember our original formula. Sum of alpha squared equals sum of alpha whole squared minus 2 sum of alpha beta, which means we can substitute these values into this formula, thus giving us 7 equals -3 whole squared minus 2 sum of alpha beta. Evaluating further, we end up with the answer of 1. Next, we need to find our original quadratic equation, which means we are to write x squared minus sum of alpha times x plus sum of alpha beta equals 0. Remember that sum of alpha is minus b by a, which is why we have to put this minus over here. And after we substitute in the values, we end up with x squared plus 3x plus 1 equals 0. For our next example, we have the quadratic equation ax squared plus bx minus 16 equals 0, whose roots are alpha and beta. It's given that sum of alpha equals minus 1 by 2 and sum of alpha beta equals minus 8. We are to figure out the value of a and b. Since we've been given these two information, we'll need to rewrite our quadratic in such a way such that the coefficient of x squared is 1, which means we end up with x squared plus b by a times x minus 16 by a equals 0. Next, we can use the very first formulae we learned to replace these with this. Evaluating further, we get a equals 2, and substituting this in, we get b equals 1. And thus, you have your answer. And finally, we have our last example of the video. We have the equation x cubed plus ax squared plus bx plus a equals 0, with roots alpha, beta, and gamma. And it's given that a and b are real and positive numbers. Find sum of alpha and sum of 1 by alpha in terms of a and b. Okay, so we need to find the sum of alpha. We can write down our original formula, sum of alpha equals minus b by a. Keep in mind that this particular b by a does not belong to the question, but the formula instead. If that's confusing, you can think of the minus b by a of the formula as the second coefficient or the first non-1 coefficient. Basically, you can imagine the general form of the polynomial as x cubed plus c1 x squared plus c2x squared plus c3 equals 0, where the coefficient of x cubed, or as a matter of fact, the coefficient of the highest power term of any polynomial, is 1. But you can ignore everything I said if that's too much as well. Just stick to whichever is easy for you. Anyways, since the sum of alpha is equal to the negatives of the second coefficient, we can write this down as minus a. Next, for the sum of 1 by alpha, write down the formula we learned for cubic equations and substitute in the appropriate coefficients, resulting in this. Easy, right? But wait, there's more. For the second part of this question, we also have the following. Given that sum of alpha equals sum of 1 by alpha, figure out if the polynomial has complex roots or not. Now, if you don't know what that means, it's when b squared minus 4ac is less than 0 of quadratic equations. But this right here is a cubic, so you can't rely on that. We'll have to be more smart about this. Let's try something like this. Since it's already given that the sum of alpha equals the sum of 1 by alpha, we can generate a substitution like this. Then, we can try establishing our sum of alpha squared formula. If we substitute in the values, we end up with this. While getting the minus a squared might not ring any red alerts right from the get-go, I'd like you to recall that the sum of alpha squared is actually an expression like this. Look, it's a sum of squared numbers, and if you know your math right, it is absolutely impossible to get a negative number if we square numbers, unless we square a complex number, such as this. And since it's already given that a and b are positive real numbers, it's also impossible for a squared to become a negative number to cancel out the minus sign outside. As such, we can conclude that the polynomial x cubed plus ax squared plus bx plus a equals 0 does indeed have complex roots. Go ahead and look back and forth through this video to really absorb what's been shown. To summarize, we've learned how to find the sum of alpha squared by using the sum of alpha whole squared for both quadratics and cubics. And it also turns out that it can be applied to higher polynomials as well. The same thing applies to sum of alpha cubed. Then, instead of going to higher powers, we went down to look at the sum of 1 by alpha and how it doesn't need extra tricks to figure out. However, we do need to take into consideration how many roots our polynomial has before deciding on which version of the formula to use. Finally, we also learned that the sum of alpha to the 0 is equal to which degrees polynomial we're dealing with. And with that, that's it for the video. Next time, we'll be covering how to evaluate sums of higher degree polynomials without even relying on long derivations to figure out more complicated formulae. Until then, ciao!